Backlog management today is highly fragmented. Sales teams, operations, plants, and vendors often work in disconnected systems, relying on spreadsheets, emails, and offline reports to monitor delivery status. This creates delays, duplicated efforts, and inconsistent information across stakeholders, ultimately leading to last-minute escalations, costly expedite shipments, and higher operational expenses. This presents a strong opportunity for machine learning. The problem is well-defined, with a measurable financial impact through expedite costs. Machine learning can analyze historical manufacturing, shipping, and order data to anticipate risks before they occur. And importantly, this is a problem that matters to all stakeholders. Sales teams, operations, vendors, and customers all require accurate and reliable delivery information to plan effectively. The objective of this project is to develop a machine learning model capable of predicting which orders are at risk of missing customer-requested delivery dates. Success would be defined by measurable reductions in expedite shipments, improved delivery reliability, and greater stakeholder satisfaction. Outcome metrics: reduction in missed commitments, lower expedite spending, and improved SLA performance. Output metrics: precision and recall of the model in accurately flagging at-risk orders. Factors relevant to this model include manufacturing lead times and production delays, shipment and delivery timelines including carrier performance, plant location and distance to the customer, order processing delays such as approvals or incomplete documentation, vendor confirmations and responsiveness, customer requested arrival dates and urgency, seasonal effects such as quarter-end surges or holidays, past expedite or ad hoc request history. The proposed solution is a supervised machine learning model trained on historical backlog, order, and delivery data. The model will evaluate features such as manufacturing lead times, shipment timelines, vendor behavior, plant location, and customer requests to predict orders at risk of delay. Validation begins with analyzing the data to identify the most relevant features. For example, we expect vendor responsiveness and manufacturing lead times to be highly predictive, while seasonality and quarter-end effects provide important context. The model must also distinguish between standard expedite services, which have contracted vendor rates and predictable timelines, and ad hoc expedite requests, which require case-by-case vendor quotes. These ad hoc requests introduce uncertainty, longer response times, and higher costs, and therefore represent critical features in the prediction process. The results will be presented through a dynamic calendar dashboard, which provides stakeholders with clear visibility into at-risk orders. Feedback from sales, operations, and vendors will serve as an iterative validation loop, ensuring the model improves accuracy and aligns with business needs over time. From a system design perspective, the model should be deployed in the cloud, enabling integration of multiple data sources and accessibility for all stakeholders. Training should occur offline, with retraining scheduled quarterly to incorporate new data and capture differences between standard months and quarter-end periods. Predictions should be generated in batch, for example on a daily basis, to update the backlog dashboard. Real-time inference is not required, as backlog management decisions are typically reviewed in daily or weekly cycles. Several risks must be anticipated. Training serving skew may occur if pre-processing pipelines differ between the training data and the production environment, resulting in inaccurate predictions. Latency is less critical because predictions are batch-based, but the integration of multiple enterprise systems could slow updates. Data drift may arise if new vendors are introduced, if existing vendors subcontract to less reliable partners, or if manufacturing is outsourced to plants with longer lead times. These shifts alter the input distributions used by the model. Concept drift occurs when the relationships between features and outcomes change. The COVID-19 pandemic is one example, when transportation timelines shifted dramatically. Rising fuel prices can also alter carrier choices and delivery times. Additionally, shipments of fragile equipment, requiring temperature control or zero vibration handling, introduce new delivery requirements the model must adapt to. In such cases, prior assumptions no longer apply and the model may underestimate risk. Mitigation strategies include monitoring input distributions, comparing predictions against actual outcomes, and scheduling regular retraining quarterly or triggered by major shifts in operations or the external environment. In conclusion, this project applies machine learning to predictive backlog risk management. By analyzing factors such as manufacturing lead times, shipping patterns, vendor performance, expedite scenarios, and customer requests, the model identifies orders at risk before delays occur. When combined with a dynamic calendar dashboard, this provides stakeholders with actionable insights, enabling earlier interventions, reduced expedite costs, improved SLA performance.